What's up everybody? Welcome again sa isa na namang kahindik-hindik, kagilagilalas at hindi ka panipaniwalang episode ng Food Physics. And for today, we will be discussing geometric properties of food. Ano po ang kinalaman ng picture na to? Well, wala lang except that merong mga shapes dyan. Geometry, okay, yun lang yung connection niya talaga. I just wanted something a little light, no? For this set of slides. So anyway, sige, let's start. Okay, bakit nga ba mahalaga ang size and shape of the food or the particles that make it up? No? So whether we're talking about things visible with the naked eye, such as when sorting fruits by size, depending on market requirements and to fit them neatly into boxes. Okay, kasi syempre, di ba usually when you buy your fruits na in-import from other countries, they would come neatly packed in boxes where they're pretty much almost the same size. And in fact, sa puno, hindi naman ganun. Merong parang sa itlog, may small, medium, large, and so on. So, may sorting and grading na nagaganap para magiging magkamukha sila. On the microscopic scale, okay, we have here a figure from a study where they found out that the particle size in chocolate bars inversely correlated with taste and mouth feel. No? So that means larger particle sizes would mean lower scores for taste and mouth feel. And of course, if you eat a lot of different kinds of chocolate, you'd probably know the difference between the ones that you like and you don't, and you try to maybe correlate that to particle size and find out na, ganun pala yun. Okay, so we have here the different particle sizes of food particles, of course, from the milli to the micro to the nano scale. So as you can see, maraming molecules and even the level of atoms almost. So we have here, starting from the right side, yung pinakamalalaki, we have the cells, starch grains, and then all of our microbes you're probably familiar with. And then we have the molecules such as glucose and water and stearic acid. So even though ganito nakaliit, no, actually yung pinaka-itsura nila, yung pinaka-geometry nila, still play an effect, no, on whether or not yung properties nila would be determined by that. So we'll try to look at some of them. Also coming from yung medyo mas malaking sizes like actual pieces of fruit. So here you can see examples of adjectives that you can use to describe the shape of certain fruits. So nag-sensory evaluation naman kayo, descriptive analysis, so you probably know how to use these, no? So as you can see, for example, for specific fruits, apples, apples can be described by shape as either round, oblong, oblate, conic, unequal, oblique, or truncate, and so on. Pati sa cross-section nila, may mga description din. So definitely, if you're gonna put these fruits or maybe root crops in a box or classify them, you'd want a certain classification scheme, and these descriptions could be one way of classifying them. No? Lalo na yung sa grading, they would maybe want certain shapes less deformed to an extent. No? So these things would be very useful in that case. So let's have some definition of terms muna, no? Since usually kapag we're dealing with geometry of smaller stuff, we're talking about particles. So dispersed systems are those composed of particles surrounded by a continuous medium. Most common would be your powders, which are actually solids dispersed in air. Those are individual particles with air in between them. Okay, so they're not per se solids as you would remember from yung discussion natin on density. We also have equivalent particle size, which are hypothetical dimensions used in modeling, na yun yung i-consider mo equivalent size ng particles. At equivalent sila dahil same ng volume or surface area as the subject. Kasi as we know, in reality, yung particles mo, hindi yan totally pare-pareho ng size and shape, no? Like if you have your granulated sugar, for example, examine them under the microscope and they're not likely to be exactly the same. So you assume, halimbawa, that your system has a uniform particle size na equal to this equivalent particle size that you will use for the sake of modeling, na i-assume mo na kunwari lahat ng particles mo ay of the same size and yun ay katulad ng equivalent particle size. Similarly, for equivalent diameter, for na mag-a-assume ka ng hypothetical geometry, no? Like perfect sphere, having the same properties as a sample. Kasi as we know, for example, hindi naman perfect sphere for yung mga particles mo, pero for the sake of modeling, you would assume that they would be, kung gagawin mong force fit mo into a sphere, yung isang particle, ganun yung magiging diameter niya, no? So, and lastly, we have specific surface area, which is a surface area of either the individual particle or the bulk material as a whole. So if it's the bulk material, it's a total surface area exposed to the hollow spaces, meaning to say, if you have, let's say, isang kutsarang granular sugar, if you were to compute the total surface area of each particle exposed to air, not counting yung interfaces kung saan magkakadikit sila, okay, pero yun lang mga naka-expose, then that would be your specific surface area for bulk materials. Okay, so we'll just look at different types of dispersed systems. First would be solids in gas. This would be mostly your powders and bulk goods such as starch, or even yun nga, sa mas malaking scale, yung mga soybeans, o kung gusto mo local, yung mga munggo nyo, ganun, kidney beans or whatever, dried beans. So yun, no? Those are examples of solid in gas. Solid in liquid, typically called suspensions. These include ketchup, chocolate drinks, and yeah, liquid chocolate pag natunaw siya, and aqueous starch solutions. Liquid in liquid, so these are typically your emulsions. You can have your water in oil or oil in water, and examples, alam niyo na po yan. We also have liquid in gas, typically your aerosols. So when you press a spray can containing liquid and it sprays that into the air, then it becomes an aerosol. So typical food applications are sprayed coatings. Like for example, yung mga pan greaser na aerosol spray type, okay, or yung mga ginagamit siguro sa baking na parang spray paint pero edible, okay. You also have gas in liquid, so these are your foams, whipped cream, ice cream, and your egg whites. And gas in solid, which are your solid foams such as your marshmallows, breads, and food cake. So typically yung mga merong mostly may air hole sa loob, okay, yung mga spongy yung itsura. And sa case naman ng marshmallow, of course, na sobrang liit nung air pockets that you don't really see actual air pockets that much, but still, that's a gas in solid technically. Okay, so ito naman yung cheat sheet para dun sa mga equivalent na pinag-usapan natin kanina. So if you want to know the equivalent diameter of, if you know the volume of your particle, let's say average volume, so you can use cube root of 6b over pi. Hindi na natin titignan yung mga derivations nito, pero at least we know na ito yung gagamitin natin if you want to convert. Okay, surface area equivalent sphere. So the equivalent diameter would be equal to the square root of the area over pi. Projected area equivalent circle, you have your projected area S, so 4S over square root of 4S over pi. And then perimeter circumference equivalent circle, yung diameter naman niya would be equal to U over pi, where U is the perimeter of the projection area. So we'll discuss projected area in a while. So simple lang naman yung konsepto ng projection, no? You have a 3D object and you say reflect light, you shine light onto it, onto a flat surface, and it would create a two-dimensional shadow. And yung two-dimensional shadow na yun yung pinaka-projection mo. And yung dimensions doon yung mini-measure mo. So for example, if it's a 3D, kukunan mo ng perimeter, then kung ito yon, yan, susukatin mo yung perimeter ng whatever na yun, no? So typically, ganun din naman ang ginagawa sa maps. You're flattening it into a two-dimensional space, and you can measure distances on that flattened dimension. So that's the same principle. Of course, you have to make sure na yung projection mo ay tama yung pinaka-magnification, because as you know, if you shine a flashlight onto something, no, pag nilalayo mo yung flashlight, lumalaki, lumalapit, or lumiliit din yung shadow. So one way to do sizing by image analysis is by measuring, of course, in dimensions niya when projected, no? We have here the major diameter, A, the intermediate diameter, B, and the minor diameter, C. Okay. So obvious from this one, para siyang length, width, and height lang, no? Taken at a 90-degree angle from each other, and each one being the shortest length that would encompass the whole projection. Okay, so just imagine if you had a three-dimensional rectangular solid, and you would take at the longest dimensions niya from each side, no, when you rotate it at 90 degrees. So for calculation purposes, these three dimensions are usually used to compute for either the arithmetic mean or the geometric mean, which can be used in analysis requiring the transformation of these data into equations. On the other hand, another definition would be this one. So this set of three diameters, ferrite, Martin, and major. So the major diameter would be, for example, in this projection of the irregular shape, major diameter would be the smallest diameter of the smallest circumference circle that would enclose the projection. The Martin diameter, on the other hand, is the diameter which cuts projected area into equal area parts. So this may or may not be the same as the major diameter. And the ferrite diameter is the height of the projected area from top to bottom ng iyong projected area. Napakarami nating kinukuhang mga equivalent this and that, no? And of course, again, these are used for modeling. One of them is the physical equivalent diameter, which is you assume a hypothetical spherical particle having the equivalent physical property or displaying a certain physical behavior as your irregularly shaped sample. So an example of this would be if your physical behavior is terminal velocity, you would want a particle, a spherical particle that would exhibit the same terminal velocity as kung ano man yung hugis ng particle dun sa system mo. Okay? So, usually ginagamit po iyon, for example, sa sedimentation velocity for calculating how long sedimentation takes place in a certain suspension, no, na magsettle sa bottom yung solids. So as you can see here, that equivalent diameter in this case, mathematically derived, is equal to the square root of 18 multiplied by the dynamic viscosity over the um, density difference between the fluid and the particle and your acceleration due to gravity. Okay, on the other hand, there's also cases wherein ang gusto mo naman is a sphere with the same light scattering property as the particle in question when you are measuring light scattering. So, hindi po natin gusto na i-memorize lang yung equation, but for us to see then that ito yung concept and application ng physical equivalent diameter na principle. In particle physics, napakahalaga ng surface area, no? So usually in terms of having a site for adsorption or for, let's say, di ba kapag meron kang dinidissolve na powder, kapag mas malaking surface area ng powder, mas madali siyang ma-dissolve sa liquid mo. So given the same mass, let's say if nag-clump yung isang powder mo, it's just one big ball and the other is fine powder. Malamang yung fine powder, mas madali siyang matitimpla. No? Like kung gumagawa ka ng, nagtitimpla ka ng milk or powdered chocolate beverage mo. So that aside, no, we have a specific surface therefore, which is either based on volume or mass, and these are simply the total surface area per unit volume or per unit mass. So this one is an instrument that can be used to measure that. Typically, they measure this based on nitrogen adsorption on the surface of the powder. Okay, and yeah, so yung uses nito mostly din sa pharmaceutical industry, other than those industries dealing with powders and such. No? So for the more advanced technologies, talagang yung particle size mismo kino-consider nila into the product processing, no? And although hindi pa ito masyadong sikat sa Pilipinas, like I think some of the manufacturers don't have much of an idea dun sa range ng particle size ng powders nila, but on let's say a molecular level, this does affect properties such as settling, how easily products can be dissolved, and the like. So if ever naglaro kayo nung bata kayo dun sa mga ball pit pool, you'd have an idea kung anong itsura ng mga spherical particles na magkakapatong. Pero kung hindi man, I have this for you, okay? Huwag kayong mag-alala, hindi ko po ito ninakaw mula sa isang ball pit pool. Meron po talaga ako nito for illustrating food engineering and food physics concepts. So notice na kapag magkakadikit yung balls, yung point of contact nila ay negligible, parang tangent lang, di ba? If you're familiar with that sa math. So in that regard, we assume that kung spherical yung shape ng particles natin, yung loss nung sa area dahil sa kanilang contact points ay negligible. And therefore, yung area ng spherical particles ay same lang ng yung total area nila is same lang nung sum ng individual areas, okay? Kasi wala kang surface area na nawawala dahil nagdidikit sila. Unlike for example, kung shape ng mga palms yung mga particles mo, okay, kapag pinagdikit ko yan, yung areas na to, tsaka ito, nawawala. Hindi na sila pwede mag-absorb, hindi na pwede doon mag-absorb yung whatever na dapat mag-absorb, no? So in that regard, the assumption here, of course, is that we're using the equivalent diameters, the dA, diba, diameter of surface area equivalent sphere, and dV, diameter of volume equivalent sphere, for our calculations of the area per unit volume. And if we combine these equations and simplify them, we simply have the area per unit volume equal to 6 over the diameter. So ito yung ratio ng surface area to volume per se. Of course, however, this is an assumption, and when in fact far from spherical yung shapes mo, and that kapag nagdikit-dikit sila ay talagang naglalock, no? Like kung cubes yung shape nyo. talaga pag nagdikit yan, wala na halos surface area na available, no? So, of course, we have to take this with a grain of salt, and these are all for modeling. So, ano ba yung purpose ng formula na to? So, we can use it for rough calculations. For example, you want to know what would be the mass, specific surface per unit mass of powdered sugar. So if we are given, for example, the assumption that you have uniform spherical particles with a 10 micron diameter, a density of 1.5 tons per cubic meter, or about 1.5 grams per ml, and the bulk density, which is, di ba, yung kapag may hangin siya, ang kanyang density ay 700 kilograms per cubic meter na lang. So, less than half kasi nga may hangin doon sa in-betweens niya. Okay? So, we start with the AV equation and replace the D with the assumed diameter of 1 micron. Therefore, your AV then is equal to 6 times 10 to the 5 meter negative 1. Then you plug that in here. You put in the real density of the sugar so that you get the per unit mass na density ng powdered sugar. Kung walang hangin, ito ay you have dito, yung available mo na surface area ay 400 square meters per kilogram of sugar. On the other hand, if we are to assume based on its bulk density, no, yung per unit mass niya na area, then we would have higher amount of tawag dito, higher area per unit mass of 860 square meters per kilogram. Now, either way you look at it, that's a lot. So, sa isang kilong asukal na pinulbos mo, kung ilalatag mo sila, no, each particle i-roll out mo yung surface area niya. What is 400 square meters? No, that is what, more than 5 times bigger than our house, no, na floor area. Ganun kalaking floor area just from taking the individual particles of sugar and spreading them across, no. So, of course, ano bang practical use ng mga ito? You're not like really gonna take particles and then ilalagay mo sa sahig, but rather, of course, when you're looking at how much area would be available for reactions, kung gaano kabilis ma-dissolve yung asukal, so pwede mo makorelate itong mga values na ito. So although for the sake of simplicity, we assume perfect spheres, many food powders are actually crystalline particles, as we know, like sugar crystals, salt crystals. Geometric form depends on the chemical structure and the method of crystallization. That's why for the same chemical formula, you can have different structures, no? As you can see, for example, with the same sugar can be granules and like those you see in peanut brittle. On shape versus form, one form can have different shapes or proportions. For example, when you have the cylindrical form, the coin is both cylindrical form and so is the soda can, but you wouldn't say they have the same shape because one is flat, the other is tall. Okay, but they both fit the definition of what a cylinder is, no? So, but you'd rather call this one a coin shape, even though they're technically both cylinders. So examples of these foods which have different shapes and forms. So you have chocolates, butter, sugar crystals, and solidified aqueous solutions. Here are some examples of the particle forms measured through their A and B, and sometimes even their C, no, kapag hindi sila uniform about an axis. Okay, so you have a cylindrical, an ellipsoidal, and a pyramidal example. So para i-relate yung isang particle dun sa equivalent diameter niya kung gaano siya ka-close, we have what we call this form factor measurement, sphericity, no? So this is how close to a sphere that particle is, no? Kasi regardless of what equivalent diameter we use, so pwede nating kunin yung pinakamaliit na diameter ng sphere na kayang kainin yung particle na yon, and then we get that ratio. If that ratio is close to 0, then we have a needle-like shape, and closer to 1, then it's closer to a sphere. So definitely, kapag mas close sa 1 yung sphericity, then yung mga calculations natin ay medyo mas malapit sa katotohanan kasi nga mas close siya sa assumption natin na spheres yung particles. So ito naman ay iba pang mga definitions ng mga less common form factors used. Parallel lang sila sa sphericity, but may measure the ratio of different things like volume to volume, specific surface area, or particle surface, and so on. So I will not bore you with reading through these ones, but you can pause or check your slides and try to absorb them in concept nila. But then it's just similar to sphericity, but they are less common in terms of usage, no? So at least you know they exist, and that yung purpose nila is to compare your particle to, let's say, an ideal particle. So the roundness factor naman is an estimation of roundness from a two-dimensional point of view. Okay, so for example, roundness rather is equal to the ratio of the largest projected area of the particle versus the area of the smallest circumscribed circle, no? So I'll get something. Okay, I have here my calculator. So obviously, ang largest projected area niya is yan, no? Basta kikita yung flat side na yan, naka-project, versus ito, which is a very small projected area. Okay, and so you want to draw the smallest circle na mag-fit yung buong calculator sa loob ng circle na yon, and that will be your AC. And the largest projected area would be this one, no? So obviously that's less than 1. On the other hand, itong bola na to, na kahit saan ko siyang ikot-ikutin, okay, ay iisa lang yung projected area niya, at ang smallest circumscribed circle ay na area ay kasing laki din ang projected area. Therefore, the roundness of this one is obviously 1. Okay. So here are just some examples of sphericity values of different shapes lang, like cylinder would be 0.8, cube would be 0.8, corn kernel 0.65, the needle is close to 0, oat grains 0.55, and so on. Generally, itong siguro mga malapit sa 1, more or less naman pwede mo silang i-model to behave like spheres, no? And of course, ang importance ito, again, as I mentioned earlier, if you were to take, kung ito gagawin mong cube shape, no, tapos gagawa ka ng ball pit pool na cube pit pool, they would stack like neat blocks, and it wouldn't be as fun to play in, no? Of course, they would be deformed by the weight of the child, no, na nandun, pero you get the point. If there are no air spaces, then that affects the density of the product and how the product would settle. Especially since in most powder mixtures, for example, actually mas mahirap doon, very complex. Hindi lang naman isang particle yan, no? Yung, di ba may joke sa internet, yung 3-in-1 coffee na hiniwala yung asukal dun sa milk and sugar. If you look at that on a microscopic scale, definitely orders of magnitude yung difference ng size ng particles na yon, no? Like a sugar particle, depending on the degree of milling, could be maybe 10 times larger than the cream or the coffee particle. And of course, you want to control that. Hanggat maaari, kung may particle size reduction ka, you want your particles to be pretty much the same size as possible, even if they're made from different molecules or whatnot, no? Anyway, okay, so segue actually on to our next portion of the topic, which is particle size distribution. As you mentioned, particles are really not that homogeneous, whether they made from a single material or different materials, no? So, even for example, in a sack of flour that was milled, possible na hindi lahat ay pare-parehas ng size. And the size distribution affects, among other things, no, yung functionality ng ingredients. Like if you're gonna use flour for baking and they're not all the same size, how will that affect yung mixing mo pag gumagawa ka ng cake batter or something, okay? Nonetheless, there are methods naman to quality check the size distribution. These are simple equipment, sieves with decreasing sizes of opening, parang mga strainer or screens na sunod-sunod. You stack them on top of each other. Okay? And meron dyang, ayan, nakita niyo may parang spring, nagva-vibrate siya or umaalog para malaglag yung mga particles. So definitely, the larger particles will remain on top, and the particles that are smaller than the sieves go down to the bottom until mas stuck sila dun sa mas maliliit na sieves. No? For at least in this case, you can consider it an ordinal data wherein you have the mass for each. Kung gaano man kalaki yung sieve, lahat ng mas malaki doon, makokollect mo yung mass nila, mass fraction nila, and you can use that data to determine the particle size distribution. Okay. The way to quantify this, of course, is not just by mass, can also be by volume, area, length, or number kung kaya mo siyang bilangin. So ito yung example ng data from testing it with the setup from the previous slide. This is index category, which is, I could just consider it like the sieve number based on pinakamalaking width hanggang sa pinakamaliit. This would be the mesh width for each of the sieves. Okay. Then in microns po ito. Delta x sub I would be the difference in mesh width between the two. So 500 minus 400 is 100. 400 minus 315 is 85 microns, and so on. This would be the mass fraction nung hindi lumusot sa sieve na yon. So for the first, tama, yung hindi lumusot, no? So 0.6 grams for the first one, 2.2, and so on. This would be for a total of around 100 grams of sample. And you now have the ratio of mi over the, so what portion of the 100 grams or what percent in mass fraction form. So this is 0.6% or 0.006 mass fraction, and so on. So as we can see from these, pinakamarami, no, yung nandito sa sieve number 5. And this one is inverse naman. So, yan, kung makita niya, pag ina-adapt niya itong dalawa, they would form 1. So, cumulative naman siya. Add this to this and this would also form 1, and so on. So, on the other hand, this is the cumulative or accumulating pass-through diagram, which shows the summation of distribution functions as a function of sieve size. So, simply put, no, kapag mas steep yung slope niya, pag mas close sa vertical, then ibig sabihin doon sa part na yon ay mas maraming mass fraction noong ng particles within that size, no, leading towards the 100%. So malinaw naman based dun sa previous table na nasa bandang gitna yung particle sizes na pinakamarami. So kung hindi natin siya gawing summative, then it will be a particle size distribution. In this case, this is a smoothened histogram curve. Mas makikita din natin no, na yun nga. So sa certain mass fractions, certain particle sizes, mas maraming by weight ng particles na ganun ang size. Okay? So this is the same as the previous graph but shown in classic histogram form since technically hindi naman siya dapat smooth kasi pipito lang yung data points mo. Ini-smoothen lang niya para maganda tingnan. Modal value on the other hand simply refers to ilan yung peak niya in terms of particle size distribution. Na parang tumaas, bumaba, tapos tumaas ulit. So you consider both peaks such that this one is considered bimodal, no? Meaning to say, of course, you would expect na monomodal yan forming some sort of hill. Dahil statistically speaking, no, dapat approximating normal curve ka. In this case, of course, pwede rin namang hindi. And that depends on a number of factors like maybe ano yung ingredients mo. Like for example, if you have two major ingredients that have a very large difference in particle size and you made no attempt to make them uniform, then you'd probably have something like a bimodal distribution. So apparently, ang sedimentation pala ay pwede ring gamitin for particle size classification. But before that, ano nga ba ang sedimentation? So this could either be in liquid or in gases, in which case it's called aerodynamic classification. The principle is that we separate the particles into different classes or categories based on them having different terminal velocities during free fall in a fluid, and fluid meaning either liquid or gas. And then, of course, that happens because eventually these particles, based on their density and particle size, would have a maximum velocity from which then causes the difference in the rates at which they settle or sediment. Okay, so huwag kayong matakot sa asa sa aking ulo or dito sa dami ng equation na nakikita nyo. Just goes to say, if the goal of sedimentation is to measure particle size, then we simply look at these equations and look at what is known and what is unknown to determine what needs to be measured so that we have one variable or unknown para masukat. And definitely, the unknown would obviously be usually the particle size, no? Or so itong R, or yung particle density natin, which we could of course determine experimentally. So nonetheless, this is just to say ito principles behind sedimentation, that example here you have particle velocity as being determined by the acceleration due to gravity, particle diameter, density difference between particle and fluid, and the fluid's viscosity. Okay, so there are many ways, of course, to use these equations either manually or automated to determine yung gusto nating malaman, which is particle size or size distribution. So how this happens is that you allow sedimentation to occur for a fixed amount of time, and you analyze the sediments either by gravimetric measurement or using automated optical sensors that could relay particle size and amount para makuha mo yung particle size distribution. So air classification, on the other hand, is similar to sedimentation but is upside down. So imbis na pinapasettle mo pababa in liquid media, ang gagawin is meron kang hangin na nagbo-blow mula sa ilalim ng isang mesh screen. Okay, but of course this is in controlled velocity, and of course when particles start to lift up, mauunang umangat yung mas maliit, And then meron kang particle collection system. So obviously, hindi sabay-sabay na angat yung mga yon, and you could quantify them based on, among other things, the time na nasak in sila if it's done in batches, no? And some of the uses, of course, is in oil and seed crushing and grain processing to separate the husks and shells from seeds, grains, and kernels. So he used the difference in their physical properties to quote-unquote classify the different particles na meron doon. Ito ay pretty much similar dun sa ginagawa natin na pagbibistay ng ipa. Diba yung kapag nagpo-process ka ng mga inani mo na palay, okay, tapos nilalagay sila sa bilao, tapos ginaganon-ganon mo yung camera. Okay, ginaganon-ganon mo yung bilao. Wait lang. Okay, mag-props tayo ng bilao. So, ginaganon-ganon mo yung bilao, and then the ambient air blows by and removes the shaft, yung ipa, no, from the bigas. Okay, nagpakahirap pa ako sa bilao. Meron naman palang YouTube video. So, we can just view this one to see how that the air classifier works, more or less. Okay, so we mentioned earlier that there are various optical techniques, and one of them is microscopy. Although this one is automated, no? Hindi ka mag-e-employ ng tao na titingin dun sa slide mo and magbibilang ng I don't know what they're looking for, no, particle sizes. Of course, computers can do that better. So there are image analysis techniques. This could be considered a sort of a 2D projection based on since flattened yung images sa microscope, more or less. And you could use laser spectrometers and or digital cameras plus analysis software or artificial intelligence to individually count the particles and maybe do some sort of image transformation in case the particles are not entirely flat, no? But anyway, it's an automated analysis, and all you need to do is prepare the sample and put it there. So another specific method is the use of monochromatic laser light, which hits particles and causes the light to scatter by reflection, refraction, and diffraction. Of course, they could calculate based on the angles of diffraction, yung particle size niya, although the assumption is that the particles have a spherical shape. On the other hand, because of that, non-spherical particles will have their dimensions reported in a light scattering equivalent diameter. Thus, dun sa earlier slide natin, merong equivalent diameter for light scattering. And one solution to this is to also measure particle volume, okay, using and process this data using software para kahit hindi sphere yun, based on the volume data, pwede mong gamitan ng AI para ibigay niya yung mas totoong maybe size or shape ng particle and or yung tamang distribution data. So optical microscopy techniques have the advantage of being rapid, having results in seconds, although sample preparation may take a while. Okay. You can use this inline. So kung magawan mo siya ng hindi tulad nung sa setup na nakita niyo sa picture kanina, pwede kang mag-install nito, let's say doon mismo sa pipe or habang dumadaan yung sample mo sa yung product mo sa processing line, since it can analyze particles even in motion, and it can be used for liquids, gases, and even smaller particles of 0.1 microns. Unfortunately, the usable wavelength is limited to the UV-Vis range, NIR, UV-Vis NIR range, and very concentrated solutions may cause errors because of multiple light scattering. Since it measures light, ang flaw din niya is kung may mali dun sa pag-interpret niya ng na-measure na light. So there are also electrical techniques wherein the particles are suspended in the liquid with dissolved electrolytes and then pumped through thin tube, no? And they measure the electrical impedance as things pass through the tube, and this impedance measured changes as the particle or that's passing through inside niya ay nag-change din. And changes in impedance are recorded, and it could automatically count and classify these particles based on those changes in impedance, no? So automatic na rin siya, para kang isang gwardiya sa mall na tumitingin sa kada dumadaan sa pinto and then binibilang mo, and at the same time nagpo-profile ka dun sa mga taong dumadaan. So gas adsorption, on the other hand, as previously mentioned, which usually uses nitrogen at 77 Kelvin, a very low temperature. You form a monolayer of nitrogen gas on the surface of your solid, and based on the amount of nitrogen, you measure the specific surface of that gas. Other methods may include the measurement of the resistance of flow of the powder, which is actually partially a rheology topic, and then acoustic impedance, so using sound waves naman, and taking advantage of the physical properties and changes in sound waves because of the particle sizes of your food substance.